Now, line integrals of a vector field, this is basically why we're teaching line integrals, not defense stuff. But the goal is when you are biking, for example, you have, how would you call this, hiking, biking hobby? Sport biking? Mountain biking, yeah? So when people mountain biking somewhere, there's especially like on the edge of the cliff and stuff, there's the winds going on. And now think about how much work you need to put into biking if wind is towards you, behind you, so it's helping you, or perpendicular to you and you're almost falling off the cliff. That is what we're going to have to calculate, because if you want to ship a satellite into space, you have to calculate not only gravitational forces, which is going against the ship going up, but all the wind and radiation and all of that stuff. So what I mentioned in my class on Thursday was, this material is hard because whatever people who don't do STEM call, oh, this is not rocket science, this is rocket science. So you finally grown up enough to learn what is rocket science. This is what it is. Line integral in the vector fields, triple integrals, is how rockets are created, how space is described, gravitational forces, black holes, and electromagnetic forces, and so on. So we're finally learning rocket science, and that's pretty cool. You can tell your parents, which are visiting this week, in general, that you finally got into level of STEM when you openly can say, I'm learning rocket science now. But how many years it took you to get here? So it's even hard to explain to not STEM people what are we doing right now, and that is what rocket science. So I will show you the animation first to make it look awesome. This is the vector field F. We already know the notation. And then, for example, you're going from A to B. Imagine those vectors are either wind or gravitational forces. When you go from A to B, they will be either helping you or against you, or no attention at all, which is perpendicular. So this is what we're trying to calculate. This green part is how much work is done by you going from A to B against the wind, with the wind, or perpendicular to the wind. And that's why line integral is being involved, because that is the area above the curve or below the curve. Look again. So I'm going from A to B. Sometimes wind is helping me. So it's going to be positive, and that's why it's going to be above the x-axis. You see, it's going to be positive first. Let me see. It's keep accumulating. Accumulating, it's positive, but then it's going to go against the vector arrows. So it's negative, and at the very end, it is also negative. So this is what we're accumulating here. As a computer game idea, when you're walking as a character in a computer game, you're collecting all the arrows on the way, like coins. If they are against you, that will be lots of work to be done. So you're collecting them all, and at the end, you will sum up the sum. If there's so many of them against you, the total result will be negative. If there's more of them with the same direction as you, positive, perpendicular to you, 0. So that's a pretty cool idea. And then one more is, I already showed you this one. Same. What is a square if you drop it on the vector field? Imagine it's a magnetic forces dragging you towards the black hole. This is a piece of paper dropped into the black hole. You saw it in the sci-fi movies probably, that it stretches the existence of the surface when it goes towards the middle of the black hole. So this is what we're trying to calculate, how the body will be changed, how much pressure the space satellite will be taking on the surface area when it's going through the gravitational forces and radiation. All of this is exactly what we're doing right now. Yes?
So for the previous one, for the graph that they had, when it equals or at least approaches the 0, like the axis, does that mean it's perpendicular?
It's getting more and more perpendicular. At 0, it's perpendicular and then changes back. Yeah.
Is that like what would, so because that's the angle, but like.
You see this one? This one looks like 0. This one is definitely perpendicular. This one is less perpendicular, becomes negative, perpendicular again. So now see how they're gonna collect.
So is it like the
see?
Is it like the dot product between the
yes, exactly. Yeah, you're right. It's all coming with dot product, and I'll show you right now. So he's right. Positive areas is when you're going towards the same direction. 0 it hits you perpendicular, negative, against you. Okay, let's do it.
This is scarier than Halloween.
Oh, this is one is also a very nice explanation. Again, if it's going perpendicular, so positive, 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 then perpendicular, and so on. So it's pretty cool. It collects all the arrows on the way like in a computer game, and the result will be either positive or negative or zero. Collecting something on the way is integration, by the way. It's integration. That's exactly how we used to collect stupid rectangles with the left endpoint and right endpoint and so on. We were doing integration. So, official, I just showed you such impressive stuff, but it's fine. Good morning. This is the idea as well. It's an animation, but the spiral we did in last class. What will happen with you biking on this spiral if the wind is blowing like this? First, it's helping you, but then becomes perpendicular, and now you're going against the wind, and then repeat and repeat. So what will be the final result? Think of collecting all the arrows as you walk along C. Definition, let's notation first. Let's see that R is a curve, x comma y, derivative, oh, that should be a vector. Derivative is going to be x prime, y prime, tangent vector. That's not new, we had this before, and here's a sketch for you. Blue is the curve. You know what tangent is. Green derivative touches the curve at one point, x comma y. Yes?
This is 13.2, right?
It is still 13.2.
It's not on the OneDrive.
It is. Oh, I did not think. Sorry. Good catch. Yeah, you can take a seat if you want. Now, hi, Asia. Very quiet, like nobody could hear it. So this is a definition. Please write down the definition. Definition of the line integral over of f over c is integral f dr. dr is a different. Let me turn off this. dr will be this tangent vector, but by chain rule we will do parametrization right now. So this is the step with parametrization over here. T is getting involved. When T is involved, chain rule happens. So this is chain rule. Chain rule over here says R should be differentiated with respect to T by the chain rule differentiating with respect to T and then derivative of T. So R prime dt, and this is the final formula. How to describe line integral with parametrization. And that's what we're going to be doing right now. I'll show you the example and hopefully it will get better.
Excuse me.
Yes?
Why was the curve a vector?
The curve A.
Go up. There. Why is it a vector?
Oh, so R is the curve. Oh yeah, you're right. It's actually not. A good point. Yeah. R is just a curve. Yes. And then the tangent vector is a vector. Yes, good catch. Now, this is the formula. Applications, this is basically the most important, are applications. If f is the force integral, which we're going to be learning how to build, which is line integral over C of going through the field F, is work done of F on C. So you are on the C, vector field is doing some work, either helping you, against you, or no relationship. Bless you, that was very cute things. And then, so that is one of the most important application. Again, work done by the gravitational forces, by the radiation, and so on, or by the water streams, and so on. Now, F times R prime inside of the integral is a number that will be dot product. So it's a number. It's a dot product. Or I like the scalar product term better. It's a number which measures how close F is to C. That is how I actually understand it better, because as a mathematician, this is the math idea. Remember, dot product tells you how parallel things are. Same here. How F is close to C. If they are parallel, then they are maximally close, even if it's different direction. Then close but negative. If they are perpendicular, it's the most not close it can be, so it's gonna give you 0, and that makes sense. So if F is perpendicular to you biking on the mountain, you don't care about that wind at all. And that's why there will be no work done by wind against you or helping you. But if F is super close to you, you literally can see your hair on your face while you're biking from the back, then it's helping you. That's how strong it is. Or maybe it's in your face, then it's against you. So that's also the nice idea from a mathematical point of view. The integral just sums up those numbers, and the final number will be either positive, negative, or 0. It will tell you if the F actually that close to C that it's doing something while you are on C. Yes.
So it's measuring how close those slopes are. Okay.
Finally, 3 scenarios you should learn. That's what going to the exam. Usually we check this idea. Think of running on a track C. So you're running. Same track, all 3 examples. 3 different scenarios of the wind. Wind is helping you. See? Wind is going in circles, helping you, magically going all the time in circles. Wind is like so. Then the number will be big and positive. So that tells you that how much work is done, positive work, it helps you. If it's against, this one is against, if it's against your running, it will be big as well, but negative. Big because F is close to C. And the previous phrase, I just explained you that this integral tells you how close F is to C. A vector field, or the wind in this case, in this example, is very close to you running on this track, but against you. So it will be still big, but negative. And then finally, perpendicular, you don't care. Yeah, it's blowing from the side, you keep running. So it's neither helping you, not against you. So that's the one that gives you 0, because it's perpendicular. Dot product part gives you perpendicular. So this is basically what we need to work through. And let's do the example. Find the work done on the force. I will just copy it, I guess. Too much writing. This is gonna be a challenge, and that's why I actually found a very cute video. You definitely should check this out. Did you see the video I posted? It's so cute. Where it is? Where is my anything? So hard to navigate. So I want to look through playlist. That is a new sub for 267. You don't have to check this one. That's for my other class. I don't plan to record the videos, to be honest. Surprisingly, my tablet does not like 1.5 lectures. It just slows down like crazy. It doesn't like it. This one, it's so cute. He explains how to do line integrals while playing the guitar. It's super cute. No.
Here's a curve.
No, I just found it online.
Long and lean. The vector field.
Well, you can listen at home.
You're supposed to find the integral.
So cute.
Well, listen up, it's Joseph Green, singing songs in quarantine. I'm here to help, so grab a new pencil.
Listen, I like this part.
No, you're scared, but take my hand.
You're scared.
I'm with you through and through. Here's what we'll do. Take the curve, parameterize. Don't feel bad if it takes 3 tries.
3 tries, he said. It takes you 3 tries to do that.
that.
Anyway, watch it. It's cute. I watched it 10 times just for fun because I really liked it. He has such a cute voice. He has more, but this one is the best one. This one is the best one. But he has more subscribers than I do. Okay.
No, this can't be. You guys are very
What do you want to ask?
Oh, I just wanted to see that again. Yeah. Or the circles.
Oh, just a second. I'll go back. I wanted to copy the example.
No. Yeah, let's watch the song one more time.
So, this one. Let's do this example with Parabola. And in that song, he says, "You are scared, but take my hand." Let's do the parametrization together, and it will take you probably 3 tries to do it. It's exactly very honest. Oh, come on. Idea. Sometimes it does it. Let's see. No, I turn off. It sometimes needs to restart. It wants me to upgrade to Windows 11, and it makes it slow on purpose. I can see that.
Oh, wow.
That is very mean.
That's really rude.
Yes.
I'm not surprised.
I'm not surprised either. Okay, here you go. Copy the example, and who wanted circles? Here they are. Find the work done on the force. So you figure out the force. Some kind of magnetic field or radiation is described as x sine y, comma y. Each point gives you a vector, if you remember, with a tail or that point. That's what we practiced last time. And then you drop the particle there and see what's going to happen. This is what I was showing you on the first lecture of vectors, the first weeks of this class. I was showing you animation, what happens when you drop the ball, when it's going to go, where it's going to go. Depends where you drop it, and depends where the little arrows are pointing. But it's interesting how much work it will be done if particle it actually moves by itself with the motor, for example, or you are biking through the field. Will the field help you? Will it be against you? Perpendicular? It will be changing through time. So you will collect all those changes, and the final result will tell you the answer, positive, negative, or not. So it's going through the parabola. Let's do it. Example. No yawning, please. Yeah, I'm also sleepy. Let's sketch the graph. What?
Can we just sleep then?
No.
Do a group nap session.
Oh my god.
I would kill for a nap. I just woke up.
So,
I love a nap.
you guys don't get distracted. Stay strong. We are drawing a parabola y equals x. Y equals, that's fine. At 1, it is 1. So 1, 1. And then at 2, it is 4. Those are my end points. It literally tells me the end points from 2. And the particle only moves from these two, between these 2 points on the parabola, along the parabola. That's important information. And parabola is y equals x squared. So in general, any random point can be described using parametric equations, but we need to figure out how to do that. For any point, for any input x, output is x squared, right? But how to describe it using t. And that's what parametrization is. Parametrization. We have to figure this out. So let's do that. Step 1 is a picture. Step 2 is parametrization. Parametrization. The simple one so I gave you typical one for circles, ellipses, for parabolas and stuff like that. The simple one is actually very kind of stupid, but it works. You call x to be t, okay, so you just put t here. Guess what y is going to be? T squared. T squared, duh, that's all. So it's kind of, the funny part, the easier it is, the more confusing it is. So people stuck usually just looking at this. That's it? You just call t and then t squared? Yes. It works, but you need to figure out what t is. Remember, parametrization needs to have right direction, and it's not infinite, so usually. T has some kind of restrictions. It definitely is from 1 to 2, but does it follow the right direction? We do have direction. It says from 1, 1, 2 to 4, because it could go other way around. So direction is here. Don't forget to check it. Let's check. When I plug 1, it should start over here. When I plug 1. When I plug 2 for t, it should be at the end. And it is at 1, it is 1, 1 squared, which is 1. At 2, it is 2, 2 squared, which is 4. So it's a good direction. If it's the other way around, you'll have to fix it yourself and figure out how to do it. Finally, let's build a new integral. We never done this before. It has completely different formula now. 3, line integral. Or integral, that's integrate. Some people do it separately, but I think we could handle it right away. The formula says integral over c f dr. That is the formula or the name of the line integral over the vector field c. C is a vector field. There's lots of wind going on like so. And this wind is described by x sine y, comma y, for you to understand, right? So while moving from A to B, from this first point to second point, I can even code if you want A and B, I wonder how this wind or gravitational forces or whatever it is helping me or going against me. Yes?
Where did you get the x squared from again?
Oh, this is how you see what parabola is. If y is x squared, for any input x, output will be x squared. So when I plug x, output will be x squared. If I plug 1, it will be 1 squared. 2, 4, 4, 18, and so on. 3.5, 3.5 squared. Yeah? So in general, you can say it's x, comma, x squared. Or you can see it like this, x, comma, y. So you plug your y, which is x squared. Integral has a formula. The formula says you need to perform parametrization, which means it's going to be dt at the very end. T is from 1 to 2. That's what we just did. Now we need to convert f into whatever we have here. The given f was x sine y, comma y. It's going to be x, but now it depends on t. Sine depends on y, which depends on t, comma, y depends on t, and it's a vector. That's not it. The formula says in this box, this part is done, but don't forget about the red part. Why am I sitting on a chair, on a table? I just noticed. Then don't forget to differentiate r with respect to t. So let's do this part. This came out from chain rule, so don't forget that. So I need to erase dt and actually perform some differentiation first. Times derivative of x prime of t, comma, y prime of t. This is a product of two vectors. What kind of product? Dot product or scalar product. So the answer will be a number. The answer will be a number. Okay, let's figure out, going a little bit faster. Let's see. From 1 to 2, dt is at the end. We know that. Now we have to change everything to be in terms of t. So x was chosen to be t. Remember? That's what we chose. It's from this parametrization over there in red. X is t. Sine of y will be sine of t squared. Right? Y is t squared. So the first vector becomes a vector of t times sine of t squared, comma, t squared. This, I think, will be very confusing. So tell me, what do you think? We renamed x to be t. We renamed y to be t squared based on the formula of the parabola y equals x squared. This helped us to create these two parametrizations where t is running from 1 to 2. Parametrization is like a new dimension. For example, time. When time is running from 1 second to 2 seconds, your particle is moving along the parabola with these equations, t, comma, t squared. Yes. No? Question? Yeah.
So, before you even add the t in, if you just have x sine y and then y as a vector, can you just replace it with the t sine squared?
Yeah.
Right away?
Your question is good. She's asking, why did they even write it down so complicated? Couldn't just write down x sine y, comma y, and then replace it with t and t squared? Sure. It's just more. No, that's not t squared. Sine t squared and t squared. Sure, it's just not very professional, I guess, to kick out t. But yeah, the point is the same. We're renaming variables in terms of t. I just wanted to show that now they depend on t, and that's why we're renaming them. But you can, actually, it's fine. Yeah, actually you can, yes. Yep.
Maybe I didn't write this down, but I'm a little confused where the sign came.
Sine came from the beginning. It was given.
Oh, I see. F equals x sine. Yes.
Yeah, it was given.
I just read that.
Now derivatives. We did not finish. There's also a tail left in red. Tail says let's differentiate x and differentiate y. But should I skip the step or show you? I don't know. Let's skip it. X is t prime, right? So I will do like this. T comma t squared, and now we're differentiating that, right? Do you know what I mean?
Yeah.
So we don't differentiate x and y. We're differentiating t and t squared. And now you're right. T is 1. T squared is 2t. It's still a vector, dt. Now the integral makes sense. This is what you saw before in Calculus 1 class. There's a t integral with respect to t. T is from 1 to 2, and all variables are in terms of t. They're just vectors. But at least everything makes sense now. Because here it didn't. Right? There's r. F depends on x and y. What is this? So that is why it's an upper level class, that even integral does not make sense from the first glance. You have to dig out the information. What is the r? What is f? What is c? How to describe it in terms of things we learned before. And we did learn parametrization before. Dot product, don't be bothered by cross product, which was hard. This one is easy. T times 1 is t times sine t squared, you can put in parentheses if you want, plus t squared plus 2t will be 2t cubed. Who failed the exam and gave me vectors the answer? Remember you did? I don't remember who did, but I'm pretty sure you remember you did. Who gave me the vector? Who gave me the vector?
Raise your hand.
It should be a number. It should be a number because it's a scalar product. Scalar means a number product. So the answer should be a number. What kind of number? Well, for now it's a function. What kind of number? Number that will tell you how much work was done by the field when you was running this stupid cross road, whatever. So that's the thing. So this number will be either positive or negative or 0, and it gives lots of information from physical point of view, mathematical point of view. Now integrate t sine t squared. What method do we use? Use up, your favorite one. I will skip that. So from now on, it's just calculus 2. It's U substitution. The answer will be minus 1/2 cosine of t squared plus t to the 4 over 4. So 2 cancels out. It will be t to the 4 over 2. Plugged 1 and 2. You can check that at home. Plug everything, and the answer will be 1/2 cosine of 1, which is some kind of number, minus cosine of 4, which is some kind of number, plus 15. This number is positive or negative. Looks positive to me, but actually we can check. But cosine of positive small numbers are positive, so it's positive, which means your wind or gravitational forces were changing on the way of your walk, but in total it helped you. So maybe you was going to the store to buy milk for your mom during the storm in Florida, and it was like, first it was away from you, and then it was helping you, so you was running. Now it was perpendicular. In total, it helps you. So like, you will, you know. That's the idea. This is pretty cool idea, because how in the world you plan to ship something into space without counting this in? Or even the ship on the ocean is always hit by waves, wind, and whatever you think about. So these things have to be considered, plus the forces that destroy the outside part of the machine you're building, either satellite or a ship on the ocean. These things being destroyed, erosions and cracks outside through overheating, salty weather and stuff like that. That should be taken into account. That's why most of the planes that fly have white color, apparently that matters, and so on. So that is important to know. So, questions? What do you think? Questions? Yes?
So is this going to be like, is this, well, because I noticed that you have the bigger than 0 at the end there. Is this going to be one of those ones where if it's negative, then we did something wrong?
No. If it's negative, means the wind was against you most of the time.
Oh, okay.
So again, I'm running a morning run in Florida during the hurricane, right? And the wind is keep changing. How is changing? Like so. At any moment, it may be like, let me show you, like this, or like that, or like this, or like that. So interesting idea. If it's perpendicular to my running, no effect at all. It just passed by. If it's towards my running even a little bit, maybe like so, it's helping me. If it's very close to me, it's helping me a lot. So it's very positive. If it's close to me but against me, it's very negative. If it's if it's almost perpendicular and against me, it's still against me, but not too much.
Yeah.
So that's the idea here.
So is this saying that like
Total.
overall
Overall.
positive?
Exactly.
Okay.
Overall, it was helping. So here is the idea. I like this image over here. See, when I'm running, say from here to here, I'm collecting this, collected. Total will tell me, was it helpful or not. Or here, look at that. Going towards the wind, perpendicular against it. Towards, perpendicular against it. So I wondered, was total helpful or not? Yeah, good questions, you guys. Definitely watch that cute video with the guitar, because actually he explains really well how to do parametrization. I really like it because of it. It's not only cute, but it's also a really good idea how to explain parametrization. Check more examples here. In these notes, because we have lots of examples over there. This is going to the exam. We always ask these questions on the test and probably final exam. Line integrals are extremely important. So you need to learn how to do that, because I just told you it is rocket science. So you need to be good at this.